So hello everyone and welcome to today's edition of our extremal and probabilistic combinatorics webinar. Before we start with the talk, let me quickly go through the usual technical stuff. This seminar is being recorded and we will later post this recording on YouTube. So please bear that in mind in case you want to ask questions. Which you can do either by just unmuting yourself during the talk, or if you have a problem with your audio, or you don't want your face to appear in the recording, you can just write it in the chat and I will read it out. And we will have a discussion at the end of the talk, and we usually do two parts. The first is recorded, and then we switch to an unrecorded mode, which is more informal. And one last thing, you can, in case you want to open the speaker's slides separately, you can find them on the seminar webpage. Okay, and now it's my pleasure to introduce Jan Grebík from Warwick, and Jan will talk about a large deviation principle for graphons. So, please.
Okay, so thank you very much. So thank you for the invitation. So let me start. So everything is joint work with O.Pikhurko, and it's still in progress, but we are writing it up, and hopefully this talk will be like a big motivation for us to finish it as soon as possible and then put it on archive or something. So what is the goal of this talk? So I want to discuss large deviation principles on the graphon space when the sequence of measures is obtained by sampling from a general graphon. So this extends the work of Chatterjee and Varadhan, who did the same thing for the constant graphon. But so we consider the question: what happens if you sample from a general graphon instead? So let me start with the motivation that motivated their work. So let's start. So we fix a parameter, so like a real number between 0 and 1. And then we consider the Erdős random graph with parameter p. So what is it? So you have n vertices and you at an edge ij independently with probability p for each pair of distinct elements I and j. So this is the Erdős random graph G and p. And now the standard like counting arguments or the expectation shows you that the expected number of edges is like p times n over 2, of triangles is p cubed n over 3, etc., etc. And all these concentrate. So with the high probability, when you like sample a random graph according to this GNP model, with high probability you will see like the number of triangles very close to the number that you expect. And so now the main question is what happens when you restrict yourself to the rare event that you have more triangles, for example. So you give me some number r that is bigger than p, and now you have the event that you have at least r cubed n over 3 triangles. So now, like, what happens? So what can you say? So first of all, what is the probability of this rare event? And second, is there some kind of typical behavior? Okay, so this is like I think this is the main motivation for their work. And now I will just comment on what is the answer, because this is like known now, and it's like a very nice theory. So first, like ideally what the answer could be, but like the reason why is just that it would be nice if the answer is like this. So ideally, asymptotically the number that this event has this probability. So when this IPR is the entropy function that just given P, what is the what is the information given P about R, let's say. And this n squared over 2, this is connected with the fact that we are talking about edges in graph on n vertices somehow. So this would be like the ideal asymptotical behavior. And then the typical behavior would be like ideally that the typical random graph in this rare event is very close in the cut distance. I will comment on it soon. Close to the Erdős Rényi random graph GNR. So basically, you will have more edges, and they will be uniformly randomly spread in the graph. That would be the typical. That would be a nice answer, right? But this is not true. This is not true. So what is the actual answer? So as I said, Chatterjee and Varadhan introduced the framework, and they studied the LDP, and then when they proved the LDP, they solved the variational problem, and they observed that, this is a very difficult theorem, but there is a phase transition. So for small parameter P, this could happen. So there are two numbers, delta 1 and delta 2, such that if you are either smaller than P plus delta 1 or bigger than P plus delta 2, then the typical graph in the rare event is close to the typical GNR graph. While, so this is called the replica symmetry, while if you are in between, then basically what you can say is that it doesn't behave like this. It doesn't behave like this. So now the exact relation between P and R was found by Lubetsky and Zhao. So here, there is P, and so if you fix P and P is small, then you just go on this vertical section, and you see that here you have the replica symmetry behavior, and here also, while in the middle there is this symmetry breaking. So there is some exact formula that computes the relationship. Okay, so this was the main motivation, and this is the success of the LDP theory. And so now what is the strategy of proving this result? So first they prove LDP. So the question is where, because as I defined the Erdős Rényi random graph on graphs on n vertices. So this is different space for each n. So you need to find one ambient space where everything lives. So this will be the graphon space. And then because it's a compact space, you have the solutions to the variational problem. So now we have to just understand what are the solutions. So this is their strategy, and they use this, and they proved all the nice results from the previous slide. So what we want to do is that we want to focus on the LDP bit, but when we sample from general graphon, let's say. Okay. So as I said, we need to first represent all the measures. So Erdős Rényi random graph, or then a general a measure from a graphon, we need to represent it on one ambient space, and this is the space of all graphons. So let me just very quickly say what is a space of all graphons without mentioning, describing. I will describe the cut distance only using the homomorphism densities, not with the actual formula, let's say. So graphons serve as limit objects for converging sequences of dense graphs. So it's important that you need to have proportionally n square many edges. Otherwise, this convergence doesn't give you anything. And what is this convergence? Well, that's the homomorphism density convergence. So I'll show you the formula on the next slide. And this is equivalent. There is the space is metrizable. So equivalently, there is some metric for which you can find the analytic formula for the metric. And now, what are actually the graphons? Well, you can represent them as measurable symmetric functions. So you get the unit interval with the Lebesgue measure, and then you just consider the unit interval squared as a domain, and then any measurable functions into the interval 0, 1. And the graphon space is then just a quotient because some functions can have distance like this cut distance 0. So the graphon space, so that's why there is this tilde, is like a quotient given this like convergence or metric. And like the most important thing is that it's a compact metric space. So basically there is a compact metric space where you can represent all the graphs and also the measures. But I will make some pictures how to represent graphs as graphons soon. Okay, so let me just recall what is the convergence using the homomorphism densities. So this Vn is a function and V is also a function. So there are graphons, and I say that the sequence Vn converges to V if for every finite graph, this quantity converges to that quantity. So you test it against each finite graph F. And what quantity is it? Well, it is the probability that a random k-tuple in the interval 0, 1 is a homomorphism from this graph F. So this thing inside represents the probability that this k-tuple is a homomorphism. Like could be viewed as a homomorphism from this graph in the graphon. And then you just integrate over all possible such k-tuples. Okay, so this extends the standard like homomorphism density or just number of homomorphisms. So when you give me a graph G, like this formula is just analytic expression to this. So this means number of homomorphisms from F to G divided by all possible maps that send the vertex set K into the vertex set N. Okay, but what you need to know is that just there's a graphon space and it is a compact with this type of convergence. But I don't think that I will only like refer to this cut distance as a metric. So important thing is it's a compact metric space. Okay, so now I said that Chatterjee and Varadhan, they proved LDP. So they need to represent, they represented this G and P, the Erdős random graph, as a sequence of Borel probability measures on the compact graphon space. And they show that this sequence satisfies LDP with speed n square. So I will define what is LDP soon. But first, I would just want to make like this standard picture how to represent a graph as a graphon. Okay, so let me just switch to iPad and make just one quick picture. Okay. Okay. Because this will be important, like to then see how to represent the more general probability measures. Okay, so suppose that you have a graph G. Oh, sorry. So G is a graph on n vertices. Okay. So let's say that we have like 5 vertices. And there are some edges. So somehow on the iPad it's kind of slow. I don't know what's happening. But anyway, if you have such a graph, then how you represent it as a graphon? Well, you just split your interval 0, 1 into 5 parts that have the same size, which in this picture is not really true. And then, for example, when you take vertex 2 and vertex 3, so there is an edge. So you will put constant one here. So it's going to be 1 here. And if there is no edge, like between 1 and 2, there will be 0. There will be 0. So I mean, this is how we represent graph G as a graphon W sub G. And of course, when you have like weighted graphs, which means that every edge has some weight, a real number between 0 and 1, well then let me just make very quickly this picture. So basically, now, for example, if this is 1 and 2, there is some weight here, which is a real number. Then similarly, you can just make the, yes, I'm sorry, I really like the iPad is not working. Now it works properly, okay. So there is this first set and the second set, and then here there will be a constant value, which is the same as this weight on the edges. And so somehow this is very standard way how to represent graphs or weighted graphs as graphons. So I just wanted to make this clear, because this is basically the main thing, how to represent these measures on the graphon space. Okay, so probably everyone knew this, but let's say that it's better to recall what I meant. Okay, so now we know that finite graph can be represented as a graphon. And so how do you represent the Borel probability measure? Well, if you give me an event A, which is some subset, let's say Borel subset of this space, well, then you just ask what is the probability that this representation of this graph will end up in this set A, and that will be the probability. That will be the probability of the event A. Okay, so this is how you can represent all the for each n the Erdős-Rényi graph inside the graphon space. And now, in the beginning, I mentioned there is this concentration, so you can now say it in the language of cut distance. So what does it say? Well, this says that for every epsilon, so P is the constant graphon, like the constant function with value P. So if you look at the ball of radius epsilon around this constant function, then the probabilities will tends to 1 as n goes to infinity. So as I said, this is the ball of radius epsilon around the constant function P, and P is the constant function. Okay, so now we transform the measures from this discrete space of finite graphs on n vertices into this big space of graphons, and we have this type of concentration, Yes, so this is just what I said. So we represented each of this Erdős-Rényi graph as a Borel probability measure on the graphon space, and we have the concentration. And now these rare events, like having more triangles or basically anything that you can think of, is suddenly a Borel subset of the graphon space, or a closed set. And you can just ask, what is the asymptotical behavior of this, basically of this sequence of numbers? So yes, when n goes to infinity. And now, okay, so I still haven't said what is the LDP, but even without that, you can still phrase what they proved, what Chatterjee and Varadhan proved, because LDP is in compact metric space equivalent to just understanding the decay of the measure around each point. So basically, if you give me a graph on U, then as this eta goes to 0, when you just check what is the asymptotic behavior of the ball around this graph on U of diameter eta, then this is the answer. So this is the answer. So this is what they proved. So I will then state it, well, what exactly I mean that as first eta goes to 0 and then n goes to infinity. But the point is that there is some this entropy function that can be defined for each U, and this is the the asymptotic tail behavior on each neighborhood of each point, basically. So what is this? What is this IP of U? Well, you just integrate the standard entropy function IP at each point x, y. And just recall, what is the entropy function? Well, given A, what is the entropy of B given A? Well, this is given by this formula. So this is like the standard. So this appears, for example, in the Sanov theorem, or like basically, this is the standard, like the function that appears when you consider questions about LDP. Okay. So now you can restate this, as I said, because it's compact metric space with the word LDP. And on the next slide, I will finally say what is LDP. So what they prove, so the LDP for the constant graphon can be stated like this. So the sequence satisfies LDP on the graphon space with this speed and this function. So it's called rate function. Okay. So this is like their result, and now our goal is to understand what happens when you sample from general graphon. So now I can finally abstractly define what is LDP.
Sorry, Honza.
Yes?
What does the word good mean? You wrote good rate function.
So the good means that it's like lower semi-continuous, the function. And again, because you are in the compact space, this just means that pre-images of sets of the form 0 up to some point A are compact. Yes. So, okay. So now I'll try to make another picture, but I'm a bit disappointed from the tablet. So how I view LDP, okay? So you have a space, some big space X. And like the input is a sequence of probability measures. No, really like this. It's really very slow, I'm sorry. And some numbers epsilon, which will be the speed. Okay, so I don't know what's going on, but okay. So anyway, so this bit are the measures, and this is the speed epsilon n. So this is mu n, and this is epsilon n, even though it somehow looks like just a curve, or I don't know. So basically, if in your space there is some very significant point x0, and all the measures concentrate like to this point, in the sense that you have some like law of large numbers or something, then you can just measure what is the decay. So you know that like for each, so this is like a metric compact space, and then when you check like neighborhood of this significant point, you know that the measures will converge to 1. And now someone gives you this rare event somewhere here, and you know that like the measure of this event will go to 0, but you want to measure how fast it will go to 0. And this is like where this speed epsilon n will play some role. And basically what you want to find, you want to like assign to each point. So each other point here, you want to assign some function I, which will be the good rate function. And then the decay of the measure of this like blue set will be measured by the infimum of this function, infimum of values of this function on points inside this set. Okay, so I'm really sorry for this picture, and I don't know what's happening with the iPad, but somehow now I will just state it formally using some actual writing. Okay, so you have a topological space, let's say compact metric space, and you have the sigma algebra. So now you want to find this function that assigns some value to each point, and this value will be the rate of like the decay of the measure on some neighborhood of this point. And you call this function a good rate function if, exactly as I said, like the compact pre-images are compact, like pre-images of like this compact intervals are compact. And now the setting is that you have the sequence of measures. Then you have some epsilon n, which will be the speed that goes to 0. And now you say that this sequence satisfies LDP on x with the speed and rate I. If, and so now, if what? So you take a Borel set F, and so you put here like the measure of this event, but you take a logarithm of it and then you multiply by the speed. So this is exactly when you get rid of like in the graphon case, there was just like this e to the minus n square over 2 times the rate function. So this is like when you basically get rid of this n square over 2, and what will remain is basically the rate function. And now you're saying that this quantity, the lim_inf and lim_sup, is bounded from below by the infimum of values in the interior of this set. So each Borel set, like for each subset, you can define what is the interior, and bounded from above by the values on the closure. Yeah, so like you give me some Borel set F, you take some smaller set, which is the interior, and you take the bigger set, which is the closure. And now the values of this rate on these two sets give you lower and upper bound for this for the asymptotic behavior of this expression. Okay, so this is LDP, and I mean I just decided to mention that in this compact metric space, this is the same as just when you give me a point X, and you take smaller and smaller neighborhoods, then the lim_inf and lim_sup of this expression will actually be the same, and it will be the rate function. So somehow it is then easy to just like you give me a point, you give me the candidate for the rate function, and you need to show that these quantities actually converge to this I of x. Okay, so this is like so far I just said what Chatterjee and Varadhan proof and what is the abstract approach to LDP. And now, finally, we switch the constant graphon P for the general graphon W. So let's do it. And now we need to sample from W. Okay. So what does it mean to sample from W? So fix a graphon. And now, like for each n, sampling from W gives you a distribution on n vertex graphs. So how do you do that? Well, you just sample n points in the like unit interval, then you check what are the values between them, because like if you sample like this is the first point, this is the second point, then there is some value of W on these 2 points, and then you just round the edges, like then you just put an edge with probability that is given by this number. So I'll call this rounding the edges according to the value. And this gives you a graph on n vertices. And somehow this process gives you a distribution on all such graphs. And then what you do? Well, the same thing as with the constant graphon. You just represent each graph as a graphon, and then you push forward the measure. So yes, so once you do this, then you obtain a sequence of Borel probability measures on the compact space. So this is like, I mean, what I just said is the same as in the constant graphon case. And again, this means that the probability of an event A is the probability that the representation of the finite graph ends in this event A. But in fact, what we need is to define 2 canonical sequences, like for each graphon. So each graphon actually gives you 2 canonical sequences of measures on the graphon space. But the second sequence for a constant graphon is trivial, so it doesn't play any role. But for us, it will be important to define both of them. So the first one will be the standard one that I try to describe, and the second one we denote this as H and W. Okay, so let me just try to make another picture. Yes. So just very quickly, this is the same thing as representing a graph as graphon. So like sampling, it will be just very similar to that. So suppose that this is the graphon. So this is the blue graphon W. And now you have this like n many points here. So let's say again 5. So what you first do, so this is like the first point, the second point, the third point, etc. So what you do is that you first sample these points randomly in this interval. And then you check what is the value, right? So what is, for example, the value of these 2 points? So this will be some real number. So this will be some number, let's say W of x1 and say x2. And then now you do like a decision whether you put an edge with this probability here. And so like using this construction, you construct the probability measures P with tilde. And what are the distribution H tilde? Well, instead of rounding the edge here, you create a weighted graph, and the weight will be actually the number, like this number, right? So you basically assign this number as a weight on this edge. Okay, so basically from graphon W, you create two probability measures. One is like first sample points, then round the edges. And the second one is sample points and then put weights on the edges according to the numbers that you see. Okay. So I hope this is also like a standard construction from how to make it from a graphon, these 2 measures. And so this is like the standard result. So if you give me a graphon W and you consider this sequence of measures, it will again concentrate around this point. And so in other words, if you sample a finite graph according to this distribution, it will be close in a cut distance to the graph that you sample from with high probability. Okay. And so let's repeat it once again. So creating this sequence requires 2 steps of randomness. First you sample this random n-tuple, then you round the edges. While getting this measure requires only 1 step of randomness. You just sample the point and then you just remember what are the values given by the W. So you obtain a weighted graph. Okay. So we started with the graphon W and we defined so far 2 sequences of Borel probability measures. And now we want to understand LDP basically of both. But the main point is that they are in some sense equivalent for speeds that are slower than 1 over n square. Okay, but first let me just say that when you consider the case of Chatterjee and Varadhan, constant graphon, then you don't see this because no matter what points you sample, what you obtain is again this constant graphon. So this sequence of measures is not interesting at all for a constant graphon. While on the other hand, when you have 0, 1 graphons, so if W attains only values 0 or 1, then these sequences are actually the same. And as I said about this sequence P, but it's true for both, they both concentrate around W. Okay. So this is like the simple fact. And now, like, what is the connection with large deviation of these 2 sequences? So why do we actually consider this sequence? Well, because it's very easy to work with this sequence, and you can show that they are like equivalent for in this LDP business for slow speed. So what does it mean? So exponential equivalence is the notion that captures this. So what does it mean? If you give me a speed epsilon n, then you say that 2 sequences of measures on a common space are exponentially equivalent. Well, if one satisfies LDP with this speed and rate I, then the other one, like if and only the other one. So, and now, like the main observation why we introduce both of these sequences is that when you have a speed that is slower than 1 over n squared, then these two sequences of measures are exponentially equivalent. So if you solve LDP for this one, which is easier, then you get LDP for this one for speeds that are slower than this, like critical 1 over n squared. So somehow this has something to do with the fact that you obtain this sequence P from H by rounding the edges basically, and there are n square edges. So this is like this is the place. Like, I mean, this is the critical speed. It's like not that surprising. Okay. And so now, once I said this, I can finally state like a general picture what happens or what you should expect when you sample from a general graphon W. Okay. So there will be one question mark, but still I call it a theorem. So if your speed is like slower than 1 over n, then like there's nothing happening. So there is an LDP, but the rate function is really concentrated on W and it's plus infinity elsewhere. If the speed is 1 over n, then there is some non-trivial behavior, and I will describe what is this rate function. If the speed is in between, then again there is some LDP, but it's kind of trivial, but it's like 0 on some set of that we call like Radon-Nikodym versions of W, and it's plus infinity elsewhere. Then the most interesting case, 1 over n squared or 2 over n squared. So in general, this is not clear what's happening, but what we can do is that for step graphons, we can prove that there is a non-trivial LDP with rate IW, which I will define. And then when you're faster than 1 over n squared, then like again, you have LDP, but the rate is 0 on some set of forbidden patterns, and it's plus infinity elsewhere. So somehow this somehow, like, I mean, there is this general case that is not clear, but otherwise you get some like description for different speeds what you should expect. Okay, so now let's see this in picture, because I think it's like much helpful to see in picture. So you pick W, and your speed is very slow. So the rate function will be 0 at W and plus infinity elsewhere. Then your speed is exactly 1 over n. And so there is some critical set of Radon-Nikodym copies of W where there is some non-trivial behavior and plus infinity elsewhere. Then once you are in between these two critical speeds, it will be 0 on this Radon-Nikodym set and plus infinity elsewhere. Then there is the set of forbidden patterns. And like for general graphon, it's not clear, while for the step graphons, you got this non-trivial rate function. And then once you are faster, it's 0 on this set and plus infinity outside, and nothing else. So this is the general picture. So now, I think like then to understand what happens in the case 1 over n squared, which is the most interesting, one needs to understand what is this set of Radon-Nikodym copies of W. So basically, this is like the new phenomena that didn't appear in the constant graphon case. And yes, so let's start with this. So the easiest way how to understand what this means is to start with a step graphon. So what is a step graphon? So we have a partition of the interval 0, 1 into k many measurable sets. And this graphon attains like a constant values on each like AI times AJ rectangle. So this is a step graphon. And now what are the Radon-Nikodym copies of W? Well, you fix any other k partition into measurable sets. So some of the sets could have measure 0, but it must be like really a partition of 0, 1. And then you just define a graphon U according to this partition B. Well, that the value at the rectangle BI times BJ is the same as the value here on the rectangle AI times AJ. Okay. And then you say that this Radon-Nikodym set is the set of all such K partitions, of all such graphons that are constructed given any K partition. Okay. So basically what we do is that we allow to like stretch or shrink this set. And then this good rate function that appeared in this speed 1 over n just measures how difficult it is to transform W to one of these like copies given by a K partition. So now this should remind you of like Sanoff theorem. So what is a Sanoff theorem? Sanoff theorem states that you have some like letters in your alphabet and you have some distribution on these letters, and then you sample, like you have K letters, and then you sample n, like a word of size of length n made of these letters, and then you observe like what is the, people call it empirical distribution of letters in this long word. And somehow this is kind of very, very similar to it, because now here you have the fixed basically probability on these sets, and now each partition here corresponds to like some like empirical measure that you can observe. And the way how difficult it is to get from these sets to this partition is measured by this function, and the function will be very similar to the Sanoff theorem. So I think that you can actually get this speed 1 over n for step graphon directly from Sanoff's theorem. Yes. Okay. So I will not make any more pictures because it's been a disaster. So so there are some prepared pictures. So again, what does it mean for general graphon? For general graphon, you're allowed to stretch or shrink the domain. So basically, you can like do something like this, or this, or this, and this will be all the possible copies of the graphon that you started with. And you just need to measure how difficult it was to like shrink the set or stretch the set. Okay. So this can be in general stated using the language of Radon-Nikodym derivative. So basically the possible stretches are L1 functions that are positive and have integral equal to 1. And then for each such function f, you can define a new graphon from the old one, from the graphon W, that attains the same values but just lives on this, like the same space but with different measures. So this measure is just the integration against f. So this is the measure that is absolutely continuous to the Lebesgue measure, right? And now, what does it mean? Like how difficult it is to get u from W? Well, you take infimum over all possible like expressions of this form, which is again something that appeared in the Sanoff theorem, but in like a discrete version. And so you take u, you consider all possible functions that modify W into u in consistence, and then you take infimum of this expression. And now this Radon-Nikodym set is just a like cut distance closure of all graphons that can be created from W. Okay, so I think this is like the very important thing that happens here. And basically now with this, you understand what the first 3 points say. I mean, the second point, basically, and the third. Yes, so the first is kind of like independent of this Radon-Nikodym thing. But why can we prove this? Well, because we work with this sequence. So it's like actually everything is made, it works very nicely when you work with this sequence in these 3 regimes. And then you just use the exponential equivalence to the original sequence. So yeah, so there's just some standard classical techniques to use to prove, to basically get these results. And already now, so one comment is that if you in the item 3 assume any speed that is slower than 1 over n, then you completely characterize LDP for this sequence of measures. So in particular, if you have a 0-1 graphon that you started with, then for the speed 1 over n square, you are basically in the item 3 because these two measures are exactly the same for such 0, 1 graphon W. Okay. So let me just very briefly mention what was the item 5. So item 5 just said that if you are faster than 1 over n squared, then there is some set of forbidden patterns where your rate function is 0 and outside is plus infinity. So outside nothing is happening. And basically this forbidden pattern just means that if you give me a finite graph and the induced density of this graph in the graphon W is 0, then it must be also true on the like given graphon U. So basically in this set are such graphons U such that whenever W doesn't see G, then U also doesn't see the graph G. And yes. So basically, like if you start with the graphon that doesn't attain 0 and 1, you don't have to care about this set at all, and it will be the whole space always. But if you have, for example, bipartite graphon, then you, for example, don't see triangles as induced subgraphs. So it's non-trivial. Like this set will be non-trivial for such graphons. And again, there's just the standard tools. Some computation gives you this item 5. So now. So now let me talk about the most interesting speed. So 1 over n squared. Okay, so what about this speed? So now why I spend so much time talking about this 1 over n, about this Radon-Nikodym inversions? Well, because there is something happening that even for a graphon that is like non-trivial, could tell you that there is no behavior for the speed 1 over n squared. So what does it mean? So I mean that this elasticity for this speed allows you to zoom everywhere inside your graphon, and each pattern will have the same weight, basically, for this speed 1 over n squared. Yes. So for example, imagine this picture. You have a sequence of graphons that are dense in the space, and you just like rescale them and put them on the diagonal. Okay. Well, but now this set Radon-Nikodym of W is just the whole space, because if, for example, you stretch this set to the whole interval 0, 1, then you will see this guy inside this set. So basically now all these elements will be elements of this set. And so like we know by the general statement that for the speed 1 over n squared, the rate function must be 0 on this set. But this set, because this sequence is dense, is everything. So for this graph, if you basically see some dense sequence on the diagonal, you get that there is no behavior for the speed 1 over n squared. Okay, so this is like one thing that happens, and it's not really clear for general graphon what is the behavior actually. But now, when you only restrict your attention to step graphons, then you don't see that many patterns where you are basically zooming. So step graphons doesn't have this rich structure of like things that you can see. Because, for example, when you have this two-step graphon with values p, q, and r, then like when you zoom to this part, you see p. When you zoom only to this part, you see q. But when you like only move this like boundary around here, you basically see the just rescaled thing, but there is not that many graphons in between that you can see. So basically, in the graphon space, this would be some closed set, this Radon-Nikodym set that connects p and q through the graphons with parameter r or something. So it would be like a curve from p to q. So this will be just the Radon-Nikodym copies. Okay. So now I want to just state what is the rate function in the case of step graphons for this speed 1 over n squared. And okay. So what you need is to basically fix a collection of all possible ways how to partition your space into either k-many sets or more generally into like fractional sets or something like that, which is nothing else than just functions. But you can think of this as like just a collection of subsets that gives you the composition of the interval 0, 1, let's say. And now, if you give me this, let's say, k-step graphon and another graphon, what will be the rate? Well, what will be the rate? So you consider all these possible like ways how to decompose interval 0, 1 into k-many sets, or more generally functions. And then you just compute the entropy function, but in the on the set ij, you will integrate against the entropy function given by the value pij. So recall that the pij is the value of the step graphon on the rectangle ai times aj. So basically what you do, you give me the graphon u, and you try to place all the possible decompositions of the interval there, and then find like minimize this value. So for example here, for this graphon P, his favorite partition is that the whole set, so there is like set A0 here and A1. And for this graphon P, his favorite partition is just the partition that the first part is the whole interval. And for this other partition Q, the whole interval is the second part. And like for anything in between, you just put the first part, the size of the first part according to the size in here, to obtain like 0 on this random Nicodim set. I mean for that particular example. Okay. And now basically you understand what is this function IW. I mean, I just defined this function. So now you see that the statement is that there is some non-trivial large deviation behavior with this function IW for step graphons. Okay. So now, okay, so I don't have that time. So let me just briefly comment how you can prove such a thing using this Chatterjee-Varadhan result, or just being inspired by that result. So the most important thing is this not many patterns that you see in a step graphon when you do this zooming. So once you have this, like once you realize this, then basically what you do is for each graphon, you assign to this graphon its favorite partition somehow, and then you modify the proof of Chatterjee-Varadhan theorem. So this is one strategy how we can prove this result. But what actually we do is that we find this more elegant thing. So first you prove LDP for bipartite graphons, and then you combine it with Chatterjee-Varadhan and to get the LDP for the space of colored graphon. So what is a colored graphon? That's a graphon with a fixed partition. So you define like a slightly bigger space, and here it's easier to prove LDP. And then you use some abstract LDP statement, which is called the contraction principle, to get this result here. Or which also could be possible, and what I wrote in the abstract, that there is this recent result of Borgs, Chayes, Gaudio, Petti and Sen. So they proved LDP for block models, and it could be that it's not really clear, but it seems plausible that with this not many patterns that you can see in step graphon, you might use their result as a black box, or maybe like use their result, and then, I mean, you need to work, and using just this thing, you might get the same thing. So this is not really clear, but is the exact connection, like how much you need to work from their results to this result. Yeah, but like we need to think about this bit. But definitely it's interesting that there is this colored graphon space that gives you that like that it's enough to use this bipartite and this Chatterjee-Varadhan result. Okay, so let me just state questions at the end. And so the most interesting question, of course, is like, if at least for the speed 1 over n, you get some like solutions to this variational problem, and you can get some possible applications. So yeah, we don't know that. And also if you can get some applications for the speed 1 over n square, but I'm not really sure how it works, because there is this like this elasticity given by the case 1 over n. So I'm not sure that you will ever obtain a like unique solution of the variational problem. This is not really clear. Yeah, but it will be interesting to understand this. And then, of course, what happens for general graphons. So as I said, we know what happens for step graphons, and it follows from this exponential equivalence that we also know what happens to the 0-1 graphons. So basically nothing happens for the 0-1 graphons. And now let me just mention that maybe if you can approximate well by step graphons, some other graphons like continuous graphons, probably enough to get LDP for continuous graphons. And like connected to this question, probably it is enough to understand like the cases when the graphon is just some very ugly measurable function. But somehow we need this graphon to not attain value 0 and 1. So it will be like 1/3 and 2/3 on this set. So maybe understanding large deviation for this type of graphons would in the end give you understanding of everything. Okay, so now I have like 3 minutes. So I wanted in the end to comment what is the connection with this work, but maybe very quickly. So basically the block model is the same as step graphon, but you have like equipartition in this step graphon, and when you sample, you always put the exact same number of vertices in each block of the step of the partition. So basically, your vertex set has size k times n, and the elements in the like you have n many like blobs next to each other, and in the ith blob will all go to the ith block, and then you will round the edges according to the probability that you see here. Yeah, so basically you put the same number of vertices in each block, and then you round the edges just according to this value. So like just last slide here, that you lose the elasticity. So there's no first layer of randomness, because you decided, okay, these vertices will go exactly to this block. So when you then try to define the rate functions, you don't consider all the possible decompositions of the interval, but just those functions or sets that have size 1 over k. So then the formula is the same, but here is just the infimum over a smaller like number of functions, like collection of functions. And then their result says that in this model satisfies LDP on this space with this speed and this rate. So this is like this is very looks very similar, but they have this fixed number of vertices in each blob, so they don't have this behavior in 1 over n. And also, like, we can have smaller value here because we take infimum over a bigger collection of sets. Okay, so this is basically everything that I wanted to say, and thank you very much for your attention. Thank you.
Okay, so could I ask people to unmute themselves and thank Honza for the talk? Thank you. So if anyone has any questions, then please just unmute yourself.
So there is something in the chat.
Thanks. Can you say, so the chat says, can you say something about how the graph looks conditional on a rare event? at least in some regimes.
No, so like, everything that you know, and this is only in the case of constant graphon, is that it will be close. Like if there are good value, if the R is a good value, like if P and R are good values, and in the rare event it behaves like this Erdős Rényi graph G and R, you can just only say that the typical graph will be close in the cut distance to this constant function R. But like, what is the distribution inside the rare event? I don't know. So, and in our case, as I said, we just did this large deviation, and now the application, that's not really clear.
Mm-hmm. So maybe also let me ask one question. I don't remember where the values of these rate functions were allowed to be 0 or infinity. But suppose so you have some sort of continuous graphon or some graphon attaining some wild graphon, and says the value 0.5 happens to be there happens to be a point, a Lebesgue point of density on the diagonal. So it's a Lebesgue point of density for value 0.5.
Okay.
So then can it be that your stretch is sort of infinitely expensive? So to get constant for your graphs to look like GN1/2, you have at rate 1/n, you have to pay infinite value.
That is possible.
That is possible, but at the same time, I guess it's
once it is in the closure, or once it is in this Radon-Nikodym closure in this set, then for the speed 1/n square, it will be immediately 0. Like for any faster speed, it will be 0. But it is possible that it will be infinity.
But at the same time, your your rate function for speed 1/n square can be 0, and there is nothing non-trivial going on in between, right?
Yes. Mm-hmm. Yes.
So Jan, thank you for a nice talk. So you were talking about different ways to sample from a graphon W. And you used the method where you just sample points and then round, and the second one where you sample points and you use the results as weights. And you also mentioned the sort of deterministic method used by Chayes et al., which is sample a fixed number of points in each block. Well, there's a couple of other things that you could try for a general graphon, right? That might, in some sense, give you a better idea from n points of what that graphon is. For example, you could sample n-1 points in the unit interval and use that to partition the x and y axes of your graphon. And then you could determine your weights just by integrating over the corresponding rectangles.
I see.
And in fact, you could get a deterministic method of doing that if you just divide the intervals equally and do the integral. And then you would have a method which sort of generalizes the Chayes et al. Method. I don't know whether this is going to buy you anything, but it seems like a natural way to do it, because after all, these graphons are they're only defined up to sets of measure 0 anyway. So in a way, taking samples of single points, doesn't seem that as accurate as you could by integrating over areas.
I see. So we didn't consider any other sampling, but I think that there were some other papers appeared that mentioned LDP and Graphons, and I'm not really sure what was their, like how they get the probabilities. I'm not sure. Yeah, but thank you.
So I have one more question. So you seem to so you have these two levels. One is the linear one, and one is the quadratic one. And you seem not to be that good at working with the quadratic one. So how far could you push it for hypergraphs where you would have many more levels of randomness and thus many more levels of these speeds?
I don't know. I never thought about this.
Yeah, I mean, yeah, if you had a 3 uniform hypergraph, could you do, that at least one case, at least one speed, which wouldn't deal only with constant or like block models?
I mean, I wouldn't really need to like spend some time thinking about what this actually means. Sampling from hypergraphons. Yeah. Yeah, but like also one thing is that for this speed 1/n, there were many results in like abstract LDP, like this generalization of Sanov theorem, which there are very like big generalizations of Sanov theorem. And then some like classical statements of functional analysis and everything. And if you combine all these big results, somehow you like know what is going on, and then you can just use these results to prove the like LDP for any graphon with the speed 1/n. But with this speed 1/n square, there is just not enough, I don't know, like big results around that would tell you what is possible, what possibly could happen somehow. Because if this set is like, as I said in the end, like just imagine the graphon that takes value 1/3 on some set and then 2/3 on some other set. If the set is ugly, like there can be on the boundary of this set, you can see all the patterns how 1/3 and 2/3 basically can like appear there. And yes, it's not really clear. Like if you see, I don't know, if you see all the patterns, then probably, no, I don't know. I actually don't know. I spent a lot of time thinking about what can happen for these ugly sets, and I don't know what can happen. For the step graphons, there will be not that many patterns, no matter what. So this is the main advantage and the reason why we understand something. Yes.
Yeah, thanks. So if there are no more questions, then thank you, Honza, and please come next week. Benny Sudakov will be talking. Mm-hmm. So thanks everyone, and bye-bye.
Yeah, thank you.
Bye.